Hello everyone, my name is Dr. Emilia Bertolo and I'm a principal lecturer in chemistry at Canterbury Christ Church University in the section of Natural and Applied Sciences. This is the first of a series of videos dedicated to acid-base chemistry. By the end of studying this topic, my aim is that you are able to identify acids and bases using different acid-base theories, and that you will be able to predict the reaction of common acids and bases in water. We will be also looking at pH, what pH is, what the pH scale means, and we'll be performing simple calculations related to the pH of strong acids and bases. We'll also look at how to link the strength of acids and bases to changes in pH. We will be looking at what affects the solubility of salts, specifically the effect of pH in the solubility of salts. And we will be studying buffer solutions. What is a buffer solution? Why would you want to know how to make a buffer solution and what you can use it for? And also examples of how buffer solutions are used in environmental and life science applications. We will also be looking at how to perform some simple calculations involving buffer solutions using something called the Henderson-Hasselbalch equation. And finally, we're going to be studying pH diagrams, and we will study how you can use what pH diagrams are and how you can use them to predict the concentration of different acid-base species in a solution. As with previous videos, these are not videos aimed at chemistry students, but those of you studying chemistry as part of your other degree. So if you have done chemistry before, you might notice that there are some concepts that I barely touch upon that maybe you have studied more either at foundation level or if you have done an A-level chemistry. That is fine. If you are curious and you want to know more, just drop me an email and we can chat about it. There are different theories that defined what an acid and what a base are. And those of you that have done chemistry before might have heard the Bronsted-Lowry theory or the Lewis theory or the Arrhenius theory. According to different theories, you can define what an acid is in a slightly different way. For example, you can define an acid as a substance that contains hydrogen and that when dissolving water releases those hydrogens in the form of ions, hydrogen ions, that we commonly call protons. You can define it not as what it has, a hydrogen containing compound, but what it can do. You can define an acid as a substance that can donate hydrogen ions to another substance. And that's another definition. And it's those of you that are familiar with chemistry, is called the Bronsted-Lowry definition. And finally, there is a more encompassing definition of what an acid is, and that's called the Lewis theory. And Lewis defined an acid as a substance that can accept electrons from another substance. And that's interesting because of the three theories, it's the only one that doesn't tell you what your compound is going to have. Like the first theory, it's called Arrhenius theory, it tells you it needs to have hydrogen and donate it as hydrogen ions. The second one doesn't tell you that you have to have hydrogen, but it's kind of implicit that you have to have hydrogen if the substance will be able to donate those hydrogen ions to another substance. However, Lewis theory, it only tells you that it has to be able to accept electrons. It doesn't preclude what structure, what atoms might form that substance. And that's an interesting point that we will pick up later. Here's an example of a typical acid, hydrochloric acid, HCl, or hydrogen chloride in gas form. Hydrochloric acid when it's dissolving water. You have the HCl, it's a covalent compound. The hydrogen and the chlorine are joined together. When you dissolve it in water, the water molecules break the bond between the hydrogen and the chlorine, and you form a hydrogen ion, H+, and a chloride and an ion. As there were different theories of what is an acid, there are also slightly different theories of what a base is. And they were formed as our understanding, or as chemists' understanding of what substances are bases evolved. Initially, the oldest definition of what a base is comes from Arrhenius, and he defined a base as a compound that contains hydroxide, the OH fragment, and that when dissolving water will produce those hydroxide anions, the OH minus. So as you notice in this base, it precludes what it has. It's a hydroxide containing compound, so it has to have this fragment OH, and when dissolving water, it liberates that OH as a negative, as an anion, as a hydroxide anion. The next definition comes from Bronsted-Lowry, which, by the way, there are two different people. They define base as a substance that can accept hydrogen ions from another substance. So they don't preclude what the base is made of. It just tells you what it can do. It can accept hydrogen ions. And this is quite a useful definition, a most common definition when you are doing acid-base chemistry in water solution. It normally covers most cases that you will encounter. And so it covers examples that in the previous theory were bases like sodium hydroxide, potassium hydroxide, but it also covers other compounds like ammonia and even the molecule of water, which can behave like bases. Ammonia is a base, a weak base, and it's not because they have OHs. In the case of ammonia, it doesn't have any oxygen, but about what they can do. They accept a hydrogen ion from another substance, for example, water. And finally, there is a definition of base as in the Lewis theory that says that a base is a substance that can donate electrons to another substance, the acid. And this is the most powerful, not always the most useful of all the definitions when you're doing especially water-based chemistry, but it's the most powerful of the definition because it both the definition of a base or an acid, according to Lewis, it doesn't tell you at all what it contains, or it doesn't bond you to a particular type of atom like the hydrogen ions. It just tells you an acid accepts electrons, a base donates electrons. Since all substances have electrons, then any substance can be defined as an acid or a base according to Lewis, depending on what it does. And more about that in a later slide. Here are a couple of examples of substances that are both bases and how they can be explained with different theories. The first one, sodium hydroxide, is the typical example of what we call an Arrhenius base. It fits really well the concept that you have a compound that has the fragment OH, the hydroxide fragment, that when dissolving water, it liberates the OH as an OH minus, as a hydroxide anion, and the sodium as a sodium plus, a cation. The second one would not fit the bill of an Arrhenius base because it doesn't contain any OH. But it does fit the bill if you use of a base, if you use the definition, the Bronsted-Lowry definition. You have ammonia, the compound NH3, that has electrons in the nitrogen that are not being used for the bond, but they are available. Those electrons can attract a hydrogen ion in solution and form this anion, NH4+, and we call this the ammonium. Sorry, not an ion, cation, ammonium ion. Ammonia cannot be explained by Arrhenius theory, and that's why the theory kind of got obsolete, because it didn't explain all the substances that could behave as bases, and that is explained by the Lewis theory, the Bronsted-Lowry theory. It can accept hydrogen ions, therefore it behaves like a base. This slide shows you some compounds that can be defined as bases and acids using the Lewis theory. If you remember from previous slide, something is an acid according to Lewis theory if it can accept electrons. Something is a base according to the Lewis theory if it can donate electrons. So Lewis theory explains how all the other compounds that were classified as acids or bases by previous theories, Arrhenius or Bronsted-Lowry, and it encompasses a whole host of other compounds that were not really covered by the previous theories. Using the Lewis theory, any compound or any anion or cation can be classified as an acid or a base. It might not be good, that doesn't matter if it's good or bad, but it can be classified as an acid, as a base. If you have a cation, for example, like here I've got the example of any metal ion you can think of, because it has a positive charge and it has empty orbitals, it can accept electrons, so that will be an acid. The same with the hydrogen ion, H+, what we commonly call proton, not very correctly, but it's a very common way of calling it. Hydrogen ions, again, it has a positive charge, it has lost electrons, that means it has empty orbitals that can accept electrons. And all sorts of compounds can be bases, are bases according to Lewis theory. You've got, for example, the molecule of water or the molecule of ammonia, where you have the unpaired electrons. Those electrons are there and can be donated to a Lewis acid. And if they can donate electrons, then they are a base according to Lewis. But also any anion, like for example the chloride anion, Cl-, it has a negative charge. That means it has electrons that can be donated to something that will accept electrons, a Lewis acid. I'm going to ask you to stop the video and have a go at these exercises. On these two reactions of these two compounds with water, I want you to identify which compound is the acid and which one is the base on each reaction. So stop the video now, please. I hope you stopped the video and had a go at the exercise. So if we look at the first compound, I didn't tell you the name before, but that's a structure of nitric acid, HNO3. So it is going to be the acid. And even if we didn't know that it was going to be an acid, if I track the changes that happen to the nitric, the HNO3 from the reagent to the product, I will see that it has lost a hydrogen, but not a hydrogen ion. It has lost the hydrogen with a positive charge. The hydrogen has left the electrons behind, and that's where you have what we call the nitrate anion. So in this reaction, the nitric acid will be the acid. And acids react with bases and bases react with acid, so that forces the water to behave like a base. And I know water in this reaction is going to be a base, because if I track what happens to the water from the reagent to the product side, I can see that has accepted the hydrogen ion, an H+, and has become H3O+. That means it has accepted hydrogen ions, so it has behaved as a base. The second reaction, hopefully you have recognized, NH3, is the compound ammonia. So if I look at the journey of ammonia from the reagent to the product side, I can see that it has accepted a hydrogen ion, this H+ species. So it has accepted hydrogen ions, it has behaved like a base. And that means that water in this particular reaction has behaved like an acid. And how do I know that? Because if I track I know that because acids need bases to react and bases need acids to react. So if I track the journey of the water molecule from the left and reagent side to the right on the product side, then I see that it has lost a hydrogen ion, and it has formed the hydroxide or hydroxyl anion, and that means it has lost the hydrogen ions, it has behaved like an acid. And it is quite common, for example, for water. It's not the only molecule that does that because it's not very good at being an acid and it's not very good to being a base, it can behave relatively easily as an acid or a base, depending on what the other compound what the characteristic of the other compound, and we call that amphoteric. Compounds. compounds that can behave relatively well either as bases and as acids, depending on what the compound they are reacting with, and they do it with ease.